Hi, welcome to Unit 63. In this unit, we're going to talk about giant stars, depending on where they come from. It doesn't matter which way they come from, whether being low mass or high mass, okay? So we're going to describe the structural changes that take place as a star leaves the main sequence, and then explain how a star transitions to helium fusion with hydrogen shell fusion. So in the core, the remnant of the hydrogen collision fusion leads to helium. So now the core is full of helium. That if the temperature is high enough, then it starts to fuse. But remember, now the temperature is high enough, probably even for the shell hydrogen to start to fuse. Describe the degenerate gas and how a star reaches and leaves this condition. Okay. Explain how giant stars move through the HR diagram. So again, the hydrostatic equilibrium, we talked about that in several units before. That's the balance between gravity and pressure. And this too will maintain the star in its form. If it's a low mass, it has to compress to higher densities to allow for the temperatures to become high enough so that it maintains its equilibrium. Whereas for a low density, for a high mass star, you really don't need that much because you have plenty of material in there. Okay. So, but this acts as a thermostat. It's very, very important to understand this. Let's say, for example, the core shrinks more. Okay, more gravity to push it to shrink. That causes the nuclear reactions rate, the rate of the nuclear reactions to increase, which causes it to heat up. So in this case, it's going to swell and push back the materials back, okay, and reduce hence the temperature, because now it expands. There is less material to do that. If somehow it expands, now the temperature will go down, which causes the temperature, the gravity now to win and compress further. So there is a kind of a balance in here. So it acts as a thermostat really to maintain the surface temperature the same. As long as it's doing that and fusing hydrogen in its core, this is a main sequence star. So we're not talking about that. We're outside of that stage, okay? So again, while in a main sequence star like the sun, for example, has this structure, and it's fusing hydrogen in its core, there is no problem, and that excess heat is escaping through the different layers all the way to the outside and then being replenished back with nuclear reactions. Now, if that hydrogen is consumed, there is no more source of heat. Now the core starts to collapse on itself, and as it does, its internal temperature starts to increase. As it increases, if it reaches high enough temperature, we'll see the limit, then helium starts to fuse. Before that, the temperature as it increases, the hydrogen that is in the outer shell of the core starts to fuse itself. So that's basically the process that we're describing in here. Again, this is the main sequence stage. As the star leaves it, depending if it's a low mass star or a high mass star, it's going to basically evolve through this red giant stage, okay, that is fusing helium in its core and hydrogen in its shell, okay, and it's bigger because of the higher temperatures that are involved. So in this case, there is not enough gravity to keep it from further expanding until it reaches higher volumes. In this case, it cannot push any further, then the gravity will keep it in that new bigger stage, giant stage, okay? Now there is another process that involves the higher temperatures, and that is the fusion of helium. You will need 3 helium atoms, or nuclei, I should say, to do this process. So 2 of them will come together. Remember, even at 10 million Kelvin, 15 million Kelvin, the temperature of the core of the sun, this is not high enough temperature to overcome the repulsion of the 2 protons from one side and 2 protons from the other. Helium has 2 protons and 2 neutrons. Neutrons that are neutral, they don't participate in the electrostatic repulsion. Okay, but two protons are positively charged and two protons are positively charged, and they will repel one another. Versus only one proton for hydrogen and one proton for hydrogen, that is high enough for them to come and fuse. So the temperature in here is high enough so that they overcome this repulsion for only a single proton. But two protons and two protons, that's 4 times as strong as this interaction in here. Okay. So you have 4 positive charges versus 2 positive charges repelling. So the 10 million Kelvin or 15 million Kelvin in the core of the sun, that's high enough for hydrogen to fuse, or even in the core of a massive stars, where through the CNO process, where those hydrogens at the end result in the formation of helium, but not helium interacting. You need higher temperatures, around 100 million kelvins, 10 times more temperature. Then in this case, the speeds are high enough so that two protons from each helium nuclei can come together and form beryllium. That's not the final stage, though. Even 4 protons, remember beryllium has 4 protons and 4 neutrons. Neutrons are neutral. We don't talk about them. We talk only about the positive charges in this case. 4 protons and 2 protons. So the forces are tremendous now that can be overcome with this high temperatures, where the protons, the helium atoms are coming with supermassive speeds that they overcome that repulsion and they fuse and form carbon. Okay. Whether we're talking about a massive star or a low mass star or a high mass star, it doesn't matter. If the temperature reaches high enough temperatures, this process can happen. So this is the triple alpha process. Alpha referring to the nucleus of the proton, nucleus of helium. Okay. Let's talk about the electron degeneracy, because that's the first stage that is really going to need to be fought. Okay. If you take marbles, for example, loose marbles. I used to have some in here. I don't know what happened to them. If you have loose marbles, that's fine. But if you try to push them against one another, contain them together, they repel one another. So this is a normal, basically, surface interactions of marbles. Think about those marbles as being electrons. Electrons, if you push them against one another, at some point, they will be so close from one another. I mean, they can probably touch, but they can never go into one another. Okay. There is an idea behind this. There is something in quantum mechanics called the exclusion Pauli principle. These types of particles, because you might thinking, oh, it has to do with the charge. No, it's not. It does not have to do with the charge, because in the case of neutron degeneracy, which is a similar process, you might think, okay, neutrons don't have charges. So 2 neutrons, theoretically, they can touch, and I have no problem with them going into one another, if you like. It's not that. It's the energy states for the 2 electrons that have to be completely distinct due to Pauli exclusion principle. And that is the idea also behind the neutron stars. So that is the electron degeneracy. This is what keeps the white dwarf from further collapse. Because gravity is so intense, there is no heat coming out now from the core to keep it from further collapse, except this quantum mechanical effect that prevents the electrons from further collapsing on one another. Okay, so you'll have a bunch of carbon atoms and probably oxygen and other elements in a white dwarf, but the further collapse is prevented from being prevented by the electron degeneracy. Okay. So for low massive stars, okay, the hydrogen fusion in the shell continues. So briefly for a moment, because in, like, for example, Proxima Centauri, which is a low mass star, in this case, once they run out of fuel, once they run out of hydrogen inside their core, in this case, they still further collapse. There is some hydrogen in the shell that's going to fuse, but that's not high enough. And the further collapse is not really going to increase the temperatures high enough for helium to fuse. So in this case, they end up with basically they're going to fade out of existence, basically. I mean, they were still a big massive ball, but their temperature starts to decrease and they stay for a long time in that state. Whereas for a big massive star, in this case, the collapse will increase the temperature for helium to fuse, okay? And that goes through several stages, okay? So again, a low massive star will probably go briefly, especially this low massive stars in here that come from less than half the mass of the sun. They don't really have high enough temperatures or high enough materials in there to cause the temperature does not reach the level where helium starts to fuse. But for the high enough massive stars, including the sun, by the way, they could go through that stage, albeit briefly, especially for a little bit more massive stars. Now, how it's going to end, that depends on their mass, okay? Either they're going to be a white dwarf or a neutron star or even a black hole. Thank you.